So chapter 5 is on normal distributions and standard z-scores. So the chapter starts off by discussing the normal curve, which is based on the more accurate generalizations, and they can usually be obtained from distributions based on larger sample sizes. Shaded areas like this represent portions of applicants who are eligible for a certain thing, whatever the target area is that you're looking at. And go into properties of the normal curve. The normal curve itself is a theoretical curve noted for its symmetrical bell-shaped form that is defined for a continuous variable. Because it's symmetrical, the lower half is a mirror image of its upper half. The normal curve peaks above a point midway along horizontal spread and then tapers off gradually in either direction from its peak. The values of mean, median, and mode are the same for the normal curve. Okay, and the importance of mean and standard deviation. You must have these values present in the normal curve. In different normal curves, so you can't arbitrarily change values, because that would create a new normal curve that no longer describes the original distribution that you're looking at. Obvious differences in appearance among normal curves are less important than expected. Once any distance from the mean is expressed in standard deviation units, every normal curve can be interpreted in the exact same way. And you can utilize this information to consult the standard normal table, by consulting the standard normal table to determine the corresponding proportion. And then go into z-scores. A z-score is a unit-free standardized score that indicates how many standard deviations a score is above or below the mean of its distribution. And in order to obtain, you'd express any original score as a deviation from the mean by subtracting the mean and then splitting the deviation into standard deviation units. And that's seen in this equation, z equals x minus mu over sigma. Okay. Z-score contains two parts. The first is a positive or negative sign that indicates whether it's above or below the mean. And then it also is a number indicating the size of its deviation from the mean in standard deviation units. They give an example here. A z-score of 2 will always signify the original z-score is exactly 2 standardized deviations above the mean. Okay, and then it goes into converting into z-scores. And then for the progress check, what would you do for each of these? You would take the the number given, subtract it from the mean, and then divide it by the standard deviation. So for the first one, you would do 135 minus 100 divided by 15, and that would give you 2.33 deviations above the mean. B, you do 470 minus 500 divided by 100. 470 minus 500 divided by 100, and that gives you negative 0.3 deviations below the mean. For C, you do 2100 minus 2180 divided by 50, which gives you negative 1.6 deviations below the mean. For D, you have 69 minus 69 divided by 3, which you'd end up with 0. So for D, the number is actually the mean. And then for E, you do negative 3 minus 0 divided by 2, and you'd get negative 1.5 deviations below the mean.